Long Valley Caldera is still doing something that rarely attracts public attention until the signals line up in just the wrong way. It keeps changing. The broad question is not whether the system is active, because the public record already makes that clear. The sharper question is what kind of activity is now being seen beneath the surface, why some recent signals look unusual, and how a caldera that formed in one of the largest volcanic eruptions in North America continues to produce seismic, thermal, and deformation changes decades after its most visible unrest began. The United States Geological Survey describes the caldera as a young volcanic system whose future activity is likely, while also emphasizing that the present setting does not point toward an imminent giant eruption. The setting itself is large enough to matter. Long Valley Caldera measures about 16 by 32 kilometers, or roughly 20 by 10 miles, and it sits east of the central Sierra Nevada. The caldera was created by the Bishop Tuff eruption, and the present landscape still shows the imprint of that violent past in the resurgent dome, ring faults, and younger volcanic features scattered along the Inyo chain. That scale matters because deformation and seismicity in a system this large can arise from several interacting sources, not just one simple magma body rising toward the surface. One of the more important recent shifts is the way scientists are reading unrest. Earlier interpretations often treated uplift and swarms of small earthquakes as straightforward signs of magma moving upward. The more recent public record, including United States Geological Survey material updated in the last few years, is more cautious and more layered. The agency says the resurgent dome has risen about 2.5 feet, or roughly 0.8 meters, since 1980, but it also states that the uplift may have been caused by either magma or geothermal water. That wording matters. It means the surface can move because of heat, pressure, and fluid circulation just as much as because of fresh molten rock. That fluid question is central to the most recent science. Long Valley sits on a coupled magma hydrothermal system, not a single isolated chamber. United States Geological Survey material on volcanic gas monitoring explains a basic mechanism that helps frame newer interpretations. As magma rises and pressure drops, volatiles exsolve, migrate upward, and can accumulate at shallower levels. At the same time, rising heat can make groundwater and hydrothermal fluids boil, release gas, and alter pressure in the surrounding crust. In practical terms, that means quake swarms and deformation can be amplified or even triggered by fluids moving through fractures, not only by new magma forcing its way upward. That is one reason Long Valley still draws attention from researchers, even when the surface looks calm. The monitoring picture is not static. In a January 1996 United States Geological Survey overview that remains relevant today, the agency described the volcanic system as still active. More recent United States Geological Survey hazard pages, updated in October 2023, keep the same basic message, but with a more refined emphasis. Future eruptions are more likely along the Inyo crater's volcanic chain than from the caldera's resurgent dome or South Moat area, and the most plausible eruptions are expected to be small to moderate, often explosive rather than supereruption scale. The hazard pages also spell out how ash and pyroclastic material could spread far beyond the vent area in future eruptions, even when the event is not especially large by caldera standards. Those hazard pages are more specific than a generic warning sign. United States Geological Survey states that during a typical explosive eruption of a Inyo vent, tephra can accumulate near the vent to tens of meters or yards in thickness, that pyroclastic flows and surges could sweep areas as far as 15 kilometers or 10 miles from an explosive source, and that downwind ash from a small to moderate eruption could still be measurable at very long distances. The same United States Geological Survey material notes that winds above the Long Valley area blow eastward more than 80% of the time, which is why aviation routes to the east are part of the hazard discussion. That is not dramatic language. It is a practical reminder that even a relatively modest eruption in a caldera system can have wide logistical consequences. The newer concern is that the system does not always announce itself with a simple, linear pattern. A year can look quiet even while the deeper plumbing remains active. United States Geological Survey's January 2026 review of Long Valley's earthquakes reported that 2025 was unusual for a different reason. It was the first year since 1980 with fewer than 10 located earthquakes of magnitude 1 or less inside the Long Valley Caldera box. And the agency noted that this quietness was not a network artifact because the monitoring system remained in excellent shape. The same report also said the last half-decade has been quieter overall, at least in terms of located earthquakes, even though the broader volcanic system remains active. That apparent quiet does not erase the deformation history. It sits beside a much longer record of uplift, swarms, and hydrothermal change. United States Geological Survey's field guide material still points to the resurgent dome's long-term rise since 1980, while the agency's hydrothermal expertise pages explain why such changes can arise from pressure and temperature shifts within shallow fluid systems. In other words, a period of fewer located earthquakes does not automatically mean the caldera has gone dormant. It may mean the active ingredients are redistributed, transferred, or expressed in different ways. That is the key point behind the recent emphasis on hydrothermal and magmatic coupling. There is also a more specific pattern behind the science of the last few years. More of the unrest is being framed as a hybrid signal. In the Long Valley setting, magma is still part of the picture, but hydrothermal circulation and gas pressure are increasingly treated as equally important in shaping what is measured at the surface. United States Geological Survey's staff profile material on hydrothermal systems says pressure, temperature, and chemical changes can provide early warnings of volcanic unrest, and that many geodetic, geochemical, and seismic signals have their origins in or are modulated by hydrothermal processes. That framing helps explain why a caldera can show visible signs of activity without immediately moving toward eruption. It also explains why scientists continue to watch Long Valley even during quieter intervals. Recent research interest is especially focused on small seismicity because tiny earthquakes can carry an outsized amount of information about the plumbing system. A 2025 American Geophysical Union paper titled Magmatic Volatile Flux Drives Non-Eruptive Volcanotectonic Seismicity points in that direction by linking earthquake timing and location to the movement of magma and exsolved gases in volcanic settings. While the public abstract does not by itself settle every detail of the Long Valley system, it supports the broader shift already visible in United States Geological Survey material, the notion that volatile transport and fluid movement can generate seismicity without requiring an eruption to be underway. That is a major change from the older habit of reading every swarm as a near-term eruptive countdown. All of that leaves Long Valley in an unusual position. The caldera is active. It has a long deformation history. Its hydrothermal system can affect what scientists see at the surface, and the regional hazard footprint remains real. At the same time, the latest public assessments do not show signs of an imminent supereruption, and the most likely future eruptions are expected to be smaller events along the Inyo volcanic chain rather than a catastrophic collapse of the entire caldera. The newest data, therefore, do not point in one simple direction. They point to a system that is still breathing, still changing, and still capable of producing signals that look stronger, stranger, or more complicated than they did when the old magma-only model was treated as sufficient. What makes that more important now is the combination of monitoring tools available across the region. Global positioning system, seismic arrays, gas measurements, and satellite-based deformation studies make it possible to see whether uplift is continuing, whether earthquake clusters migrate, and whether thermal and chemical changes are tied to the same source or to separate parts of the system. The public record shows why that matters. A single eruptive vent is not the only concern. The Long Valley area also includes geothermal fields, fumaroles, hot springs, fault zones, and young volcanic chains that can each respond differently to changes in pressure and heat. That complexity is precisely what makes the recent changes under the caldera so worth watching, because the signals no longer fit neatly into a single category. Seen together, the recent data portray Long Valley Caldera as a system where activity can be real without being simple. The caldera's shape, its 2.5 foot to 0.8 meter long-term uplift on the resurgent dome, the quieter 2025 seismic year, and the United States Geological Survey hazard outlook all fit a single broad picture. The system is restless, but restlessness is not the same thing as imminent eruption. That distinction matters because the public often treats any caldera signal as a direct warning, when in fact the stronger lesson from Long Valley is that fluids, gases, heat, and magma can produce overlapping patterns that require careful reading rather than instant alarm. The region's longer hazard profile reinforces that point. United States Geological Survey says volcanic activity and related hazards are likely in the future, but the same agency also frames the expected future activity as mostly small to moderate eruptions, often explosive, along the Inyo chain. It identifies ash fall, pyroclastic flows, and air route contamination as realistic hazards, not because a giant collapse is expected now, but because the volcanic system has repeatedly shown that it can shift from quiet to active with little public warning once the right conditions are in place. In practical terms, Long Valley is best understood as a monitored volcanic province with multiple potential failure modes, not as a single volcano waiting for one obvious trigger. The updated science also changes how uncertainty is handled. When the United States Geological Survey says uplift may be caused by magma or geothermal water, it is acknowledging a core difficulty in caldera monitoring. Different processes can produce similar surface effects. A rise in the ground, a run of micro-earthquakes, or a shift in gas chemistry can indicate magma movement. But those same signals can also reflect changing pressure in hydrothermal reservoirs. That is why newer studies are increasingly focused on separating magmatic from hydrothermal contributions, rather than assuming one explains everything. Long Valley is a textbook example of why that separation matters, because a hybrid system can look noisy without necessarily being on the verge of eruption. That interpretation is consistent with the broader public monitoring story. The 2026 United States Geological Survey note that 2025 was exceptionally quiet for earthquakes inside Long Valley does not read like a retreat from concern. It reads more like a reminder that volcanic systems do not behave in straight lines. They can shift between episodes of quake-rich and quake-poor behavior while the deeper reservoir remains active. In the Long Valley case, a quiet year inside the caldera does not cancel the background signs of a young, active volcanic field. It simply adds another data point to a longer record of alternating unrest and relative calm. The larger scientific trend is also clear in the wording used by United States Geological Survey and in the newer research language around volatile flux. Volatiles, gases, and pressurized fluids are no longer treated as secondary noise around magma. They are now central to understanding why earthquake swarms start, how stress changes propagate, and why deformation can continue even when seismicity falls off. In a caldera like Long Valley, that means a change under the surface can be meaningful even when the change is not dramatic in a classic eruptive sense. The recent findings do not suggest that the system has become more dangerous in a simple linear way. They suggest that it is more legible than it once was, and also more complicated. That evolving clarity depends on how multiple streams of measurement are interpreted together rather than in isolation. Long Valley Caldera is monitored through a layered network that includes continuous global positioning system stations, satellite radar interferometry, seismic arrays, gas sampling sites, and thermal observations. Each of these tools measures a different expression of the same underlying system. Ground deformation captures how the crust flexes or inflates. Seismicity records how stress is released through fracturing or fault slip. Gas emissions reveal how volatiles migrate upward. Thermal changes reflect how heat is redistributed through rock and fluid pathways. When considered separately, each dataset can suggest competing explanations. When combined, they define the operational picture of a coupled magmatic and hydrothermal system that does not behave in a strictly linear or predictable manner. The deformation record remains one of the most persistent signals. The resurgent dome, which has risen approximately 2.5 feet or 0.8 meters since the late 1970s, continues to serve as a reference point for long-term uplift trends. That uplift has not progressed at a constant rate. Instead, it has advanced through pulses, pauses, and partial reversals. Satellite-based interferometric synthetic aperture radar has made it possible to resolve these changes at high spatial resolution, showing that deformation is not uniformly distributed across the caldera floor. Certain sectors rise while others remain comparatively stable, indicating that pressure sources beneath the surface are compartmentalized rather than continuous. This pattern aligns with a system in which magma bodies, fluid reservoirs, and fracture networks interact in discrete zones rather than forming a single, unified chamber. Seismic observations add another layer to that interpretation. Long Valley has a long history of earthquake swarms, some involving hundreds of small events over short periods. These swarms are typically shallow to mid-crustal in depth and are often spatially clustered along known structural features, such as ring fractures or fault zones. What has changed in recent analytical approaches is the emphasis placed on the driving mechanism of these swarms. Rather than attributing them solely to magma intrusion, more recent interpretations allow for the role of fluid pressure changes, including the movement of superheated water and exsolved gases. When fluids migrate through fractures, they can reduce effective stress and trigger seismic slip without requiring a large influx of new magma. That mechanism is consistent with observations of swarms that occur without significant accompanying deformation, as well as with periods of deformation that occur with relatively few earthquakes. Gas measurements provide additional constraints that are increasingly important. Carbon dioxide emissions, in particular, are monitored in several areas around the caldera, including soil gas flux zones and fumarolic regions. Elevated carbon dioxide concentrations can indicate the upward migration of deep magmatic gases, but they can also reflect changes in shallow hydrothermal circulation. The distinction depends on isotopic composition, flux rates, and spatial distribution. In Long Valley, variations in gas output have been observed to correlate with both seismic activity and deformation, though not always in a straightforward way. This reinforces the interpretation of a hybrid system in which gas release can both respond to and influence subsurface pressure conditions. Thermal data further complicate the picture. The caldera hosts an active geothermal system, including hot springs and fumaroles, that is sensitive to changes in subsurface heat flow. Temperature variations in these features can occur due to shifts in groundwater pathways, pressure changes, or variations in heat input from deeper sources. Satellite thermal imagery and ground-based measurements have documented fluctuations that do not always coincide with seismic or deformation events. This decoupling suggests that heat transfer pathways can evolve independently, even as they remain linked to the broader magmatic system. In practical terms, it means that a change in one monitoring parameter does not necessarily predict a simultaneous change in another, even when both are ultimately connected to the same underlying source. The structural framework of the caldera plays a decisive role in how these signals are expressed. Long Valley is bounded by ring faults formed during the original caldera collapse, and these structures continue to act as conduits and barriers for fluid and magma movement. Additional fault systems intersect the caldera, creating a network of potential pathways that can channel pressure and flow. The Inyo volcanic chain, which extends from north to south along the eastern flank, represents one of the most important exit routes for future eruptions. The alignment of these volcanic features suggests that regional stress fields, not just local pressure inside the caldera, influence where and how activity is expressed. This structural complexity is a key reason why future eruptions are considered more likely outside the central dome area. The probability framework used in hazard assessment reflects that complexity. The estimate of roughly one eruption in a few hundred years under baseline conditions is not a precise forecast, but a statistical representation based on geologic history and current activity levels. It incorporates the frequency of past events, the distribution of vents, and the present state of unrest. Importantly, that probability is not static. It can increase during periods of heightened seismicity or rapid deformation, and decrease during extended intervals of quiescence. The recent quieter seismic period does not eliminate the probability of eruption. It simply represents one phase in a longer cycle of variability. Long Valley Caldera therefore stands as a case study in how volcanic systems are reinterpreted as observational capabilities improve. The changes beneath it are not isolated events, but part of an ongoing process of adjustment within a heat and fluid-driven system. The recent findings reinforce the idea that understanding such systems requires attention to detail, patience in data collection, and caution in drawing conclusions from incomplete information. The caldera continues to evolve, and the record of that evolution is being written not in a single dramatic shift, but in the accumulation of subtle, measurable changes across the landscape and beneath it.